If this is up and this is no, how is it? Oh, this is like that. Okay, and the pointer is up there. Okay. Okay. 3 remarks. First of all, I am not a historian of science. There are very well-known Smoluchowski knowers at my university, as you can imagine, as we are coming from Marian Smoluchowski Institute, and he was our professor there in Krakow, but you will hear about that later. The second thing is I'm condensed matter theorist, but working in quantum matter, so I am not soft matter man also, so I'm sorry, I don't know much about it. I'm working in superconductivity, in quantum criticalization, so if your soft matter becomes quantum, then we will meet probably. Okay? But then there won't be any liquid crystallinity. Okay? So, and now the third remark is I work at the Jagiellonian University, which is the oldest university in Poland. As you know, it is alma mater of all Polish universities. And next to you, it was established in 1364. I will talk about that in a moment. And the next, this was alma mater for University in Vilnius, which was created in 1566 by another Polish king, Stefan Batory of Hungarian origin, and another king. This university, Jan Kazimierz, which was coming from Waza family. They were intermarriage of Polish ladies, Polish grand duchesses, with some foreign kings. Then the last one, you see, the second faculty I work with at is the AGH University of Science and Technology. This university has been created in 1919, so it has 90th anniversary this year. And believe it or not, in 1917, Smoluchowski was the driving force behind creating the School of Mines, and another mathematician who comes also from Lwów, Choborski, and one geologist, Valery Goethe. Because Jagiellonian University is a classic European university. As you know, all classic European universities, they did not have engineering schools. So, of course, now we have biotechnology, we have computer science, but we have no metallurgy, no mining, and as you know, Poland is abundant in coal. So Smoluchowski, when Poland was recreated after 133 years of partition between Russia, Austria, and Prussia, then we needed the technical college, and Smoluchowski was the driving force behind this technical college. So he looms all over, even though he lived only for 45 years, as you will see. So this is the oldest college of our university. It's called Collegium Maius. Collegium Maius, which is in English, it's major college. And as you know, here is where the university started in 14th century, and it was created by Casimir the Great. And actually, that's the college. You see, it's not as beautiful as Cambridge colleges, but because it's a Romanesque style. And whereas English colleges were built 200, 300 years later. Here Copernicus studied, our best student so far, Nicolaus Copernicus studied here and graduated, and he did do PhD. He left, he studied liberal arts from 1491 to 1495. He left for Bologna and then studied Bologna, Padova, and then it was too expensive for him to pay for PhD, so he left for University of Ferrara and he graduated in canonical law. This one astronomer actually graduated in canonical law. Here are these are our founders. This is the lady which is admired. Actually, she is a saint, really. It's Queen Hedwiga, comes from the Polish intermarriage of Polish queen and Grand Duke of Hungary, who was Louis Andegawen, and she became Queen of Poland, and she intermarried the Grand Duke of Lithuania, and then this is the times when Poland was the greatest country in Europe, from Baltic Sea to Black Sea, about 2 million square kilometers in thing, and so on. Unfortunately, Ukraine was not then independent. Lithuania, they were also not unhappy. The name of the country was Polish Crown and Grand Duchy of Lithuania. And they were not so happy because they thought that the Poles dominated them, but that's a matter of history. Here is this most famous book, which was it is in the Jagiellonian library. Everything is Jagiellonian, because the king was, the Grand Duke of Lithuania was Jagiello, so Jagiellonian means coming from Jagiellonian dynasty. Here is the Revolutionis Orbium Celestium of Nicolaus Copernicus. As you can see, this is almost extinct. This thing is almost extinct. Probably. So let's do that. So as you know, the spherical. So this is Copernicus thing, and this is the original, and it has to be saved through the war. This book has a very history of its own, but I want to go. Let's go back now to Smoluchowski. This is our Faculty of Philosophy at the year 1900, whole Faculty of Philosophy. This is Faculty of Physics, Astronomy, Mathematics and Applied Computer Science in the year of 2000. So in one field whole philosophy, also embodied natural philosophy. Here is only exact sciences, and you can see how it grows in 100 years. We shall see what will happen in another 100 years. Now here is the man of here's the man. As you can see, he lived a little bit over 45 years. And of course, I could see that Professor Balau has written Marian von Smoluchowski. Actually, as you see, Marian Smoluchowski comes from very old, noble Polish family. And his father, during the time when Krakow and Lwów were in Austria, his father was a lawyer, actually responsible directly to Franz Josef der Erste, the first. And Franz Josef gave to his father another noblehood. And then so this was the second one, this form, German. And Smoluchowski personally did not like any nobleship. So when he got from Lord Kelvin the honorary doctorate at the University of Glasgow, and Lord Kelvin came to him and said, Marian, how come you have two nobleships and I have only one noblemanship? And Marian said, Lord, you know, sometimes one lordship is better than two noblemanship. He didn't like it. He was a very remarkable man, as you will see in a moment. Okay, biographical sketch. So first 27 years around Vienna, his father worked for the Kaiser Franz Josef I, born in 1872, and he, in 1898, was lecturer at the university. Father was a lawyer, a high official, okay. Mother Teofila was a staunch Polish patriot, when there was no Poland then. Through her, Marian became, as his mother, an expert pianist. Oh, should be one N. Oh, I'm sorry, there are some mistakes. He was really, so probably, when talking about him, somebody should have played piano. He actually was a master pianist in Polish folk songs, and the famous Polish composer Karol Szymanowski took some music out of the improvisation of Smoluchowski. Okay, he, of course, the sister of his mother was also pianist and singer, was living in Florence, and of course, young Smoluchowski was actually playing also in Firenze on piano. Okay, he was also an amateur. Oh, sorry, Marian Smoluchowski. Sorry, you will see why it's RM. Marian Smoluchowski was also amateur painter. I didn't put any aquarelles here. They were mainly connected with one subject, mainly with the mountains. But they were great alpinists with his brother Tadeusz. Actually, some of the first passes in Dolomites, in Italy, in the Alps are awarded by the name to them. Okay? So he did PhD in 1895 at the age of 23, and like you can see that he is already related to the subject of this workshop, namely his PhD title was Acoustical Studies of Elasticity of Soft Materials. He listened to lectures by from Stefan Boltzmann Law, by Exner, but true inspiration was coming from Boltzmann. Boltzmann was then still working in the Munich University, still hasn't come back to the University of Vienna, but Boltzmann really regarded Smoluchowski as the natural heir to this, to the logical heir to the kinetic theory. As a postdoc, he spent a little bit over a year in Paris. He said that he for the first time learned about l'esprit français. He loved it. The atmosphere. He thought Vienna was a provincial town. He stayed in the hotel in which the playwright Strindberg stayed, and Strindberg saw his name on the plate of his passport, and they introduced in his play the name Smoluchowski, and he thought that, as you know, Strindberg was a very disturbed person, so he thought it's the devil himself, it's trying to tell him something, and so on. And it was Smoluchowski who was staying back in the hotel, and his son, Roman Smoluchowski, said to that, you see, now Strindberg, even though he was very disturbed, is very well known, but Smoluchowski, who was a perfectly normal scientist, it's only known only to a narrow group of people. Okay, so he was with Lippmann on optical properties of thermal radiation. It was a little bit too late because, of course, then he went to London and Glasgow to Lord Kelvin, and he worked with those on the effect of X-rays on the gas conductivity. Later got the honorary degree from Glasgow University from Lord Kelvin. Actually, it's a very interesting story, because in the English tradition was that if you are awarded an honorary degree, no faculty can award which you belong to. So no physics faculty awarded the degree to Smoluchowski, but law, faculty of law. I don't know what is the logic behind it, but if there is an Englishman, probably, I don't know if this tradition still exists. Then, of course, everywhere he worked in both experiment and theory. At Jagiellonian University, he had a chair in experimental physics. Actually, chair in theoretical physics was another remarkable man, Władysław Nathanson, who discovered principle of indistinguishability of quantum mechanical particles 10 years before Boson. Now it's in history of physics very well recorded and very well, very well known, but of course it's too late. It's too late. Then, of course, in 1889, he moved to Lwów from Vienna. Why he moved, it's also very interesting. Here you have the name of Lwów in all possible, all main languages. And in 1903, he became professor, full professor there. In 1901, he came first. He came to Kraków, married Zofia Baraniecka, daughter of a mathematics professor at the Jagiellonian University, a real Slavonic beauty, and that's how he became interested in Kraków, I would say immediately. His wife assisted him by editing his paper and correcting his galley proofs. She died in 1959, interestingly enough, in the United States. But why, I will say in a moment. It's, okay, maybe I shouldn't talk about that. Okay, then in 1905, he made a 9-month visit to Cavendish in Cambridge. And of course, he then started going very intensively to Krakow because he became a member. We had an Academy of Science in Krakow, the oldest Polish academy, and he was becoming a member and published in that bulletin very often there, and he also was coming to Vienna. So he was chair of experimental physics in Krakow. Here you have Krakow also. Krakow, that's the true name. Here, no, this is Krakiv. In Ukrainian is Krakiv. And so on. So you can, this is English name, but you shouldn't use it because now in European Union we use original geographic names. Okay. So in 1912, from 1913, he became of charge Institute of Physics. By the way, this is the institute, the first institution which used Institute of Physics in European science, in world science. It was created in 1772. Then he became Dean of Faculty of Philosophy During the war, he commanded an artillery detachment unit guarded in Coral Bridge. He was censored the name of his soldiers and was complaining how desperate those soldiers are and how difficult is the situation of their families. Actually, his comments about living in England, he said, you know, of course, about food and about the weather. And he said if he has to judge what is worse, whether the weather in England and Scotland or the food, he thinks that the food is worse. So he was quite a character. Okay, so then he gave Göttingen lectures, and in 1917 was invited again. And I must tell you, as a student, as a graduate, I read his lectures. It's about irreversibility and statistical physics, statistical meaning for irreversibility. These are absolutely wonderful lectures. They have been translated in all possible languages. They were delivered in German. They are translated, of course, into Polish, into English and Russian. I don't know about French, but probably too. 1917, Vienna University wanted him to become chair of theoretical physics, and Warsaw University, because Poland was recreated, wanted him as a professor. So Jagiellonian University authorities immediately nominated him to become a rector magnificus, the president of the university. Unfortunately, he died on dysentery, at the age of 45. You know what it was? He was an excellent climber, and he was going back from Tatra mountain, and there was a Raba river. Of course, water was crystal clear, and he drank the water from the Raba river, and he didn't know that, because this was 1917, that the horse died during the fighting and was lying in the river for something like a week or so, so it was contaminated, water was contaminated. Of course, today they would just make an injection and he would be saved, but not in 1917, so that's how he died. It's real. 1 year later, the Swedish Svedberg, who confirmed his theory of Brownian motion, which in Brownian motion got the Nobel Prize, and Smoluchowski was absolutely sure of getting Nobel Prize. Everybody was sure, but unfortunately he didn't live to that. That's a little bit fortunate, like our history of my country. He had two children. Son Roman became American physicist in Princeton, and then at the University of Texas at Austin. Some of the solid-state physicists may know that he was with Frederick Seitz, very tightly connected, and wrote papers on group theory in solid-state physics and so on. He had also a daughter, Aldona, who was a musician also, who was again a musician. Okay, so then I said about this Smoluchowski, about that he, when he got the Nobelhood. Here is his parents. You can see this beautiful wife and this Kaiser Franz Josef, the Chancellor. Then you have again the family, and these are those two boys. Here is Marian Smoluchowski. Here is this Tadeusz Smoluchowski, alpinist, chemist, and also medical doctor. Here you have Smoluchowski with his wife. As you can see the beauty, they were very deeply in love when he was coming back from foreign trips. For example, they left children, everybody at home. She came to the station, to Lvov or to Krakow, and they were walking through the park in the woods, just showing admiration to each other before they came home. So it's a very, very beautiful love letters he wrote to her, even though he was very reserved whether he should marry, because it will interfere with his science. But once he did it properly. Here, these are his children. So now we come back slowly to physics. So these were the mountains. That's what I said. They were pioneers of skiing in Poland also, as you will see in a moment. Here, this is brother Tadeusz with his colleague climbing in Dolomites. Why do I show you that? Because a little bit personal note. It doesn't look much different from how we. It doesn't look much different how we look at our picnics or hippie looked in the 70s when we climbed in Russia and Siberia. So that's how it is. These are Dolomiti, and you see this pass. This is called 5 Fingers, Cinque Dita, which they made. Of course, it looks, but you can see the equipment in a moment. So this is in the called beauty. And his son has written, according to Roman Smoluchowski, it was in the mountains where Marian Smoluchowski could face unspoiled nature and acquire the strength for his scientific endeavors. They accustomed him to challenge, gave him satisfaction when he overcame very challenge, embellished, decorated his life with the highest poetry, the poetry of mountains. And in his words, this is the real world of Marian Smoluchowski. So here you can see a few members before the mountain expedition. Somewhat it looks kind of modern. Huh? This is the group of alpinists and so on. Here he is, well, I'm showing this because it's in Ukraine, it's Chernohora. It's the very high massive here in the Carpathian, the Ukrainian Carpathian Mountains. So it's Marian Smoluchowski. Here is the RC lakes, the Tatra Mountains, which he loved. You can see the type of equipment they had with the climbing with his wife. Here, a moment of reflection. And his aquarels were a little bit like that, and so on. Here they are studying with another professor of the University, Zachewski. Here they are before the building, before the Collegium Minus, where actually air, components of air, nitrogen was liquefied for the first time in Krakow by Wróblewski and Olszewski. They tried to do it with helium. They didn't manage because Wróblewski died of the accident during the scientific work. This is the Collegium Novum, and these are old colleges, the first campus, and so on. And Smoluchowski credo, now I'm at the end to physics. And sorry, I will read it with Polish accents, so you will have a feeling how Smoluchowski would have phrased it. Okay? They said he spoke 4 languages fluently and 2 languages, like Ukrainian, Russian also. He spoke Polish, English, German, French. And they said he spoke beautifully, but all with the same accent. Okay? So you will hear it. If according to the widely accepted point of view, narrow one-sided specialization is characteristic of modern research methods, then I must consider myself to be a physicist of the old school. This is 1913. Old school, because my personal inclinations are towards shifting my work between various branches of physics, and this applies to the use of limits, differentials and integrals, as well as to the use of or a blower. Whoever wants to produce many scientific papers should indeed cultivate a narrow limited field. O tempora amoris, déjà vu, as accurate and periodically as possible. I'm rather interested in not losing sight of the whole and in participating in progress on the entire front. Beautiful. This is really beautiful. I hope this translation reflects what he wanted to say. Now science. He published first paper at the age of 21 on internal damping in liquids. The main contribution is, of course, the Brownian theory of Brownian motion. As you know, he produced the same results as Einstein, but his method was even better, as you will see in a moment, because he was a creator of theory of stochastic processes. Then theory of fluctuations, and theory of opalescence, critical fluctuation. I won't talk about that. It's a beautiful thermodynamic theory, but it has been written in history of physics by many people. Theory of Brownian motion, as you know, the main thing that you have the mean square motion of the Brownian particle from the origin is proportional to time, and the coefficient of proportionality is the so-called diffusion constant. And then diffusion, that's the first, then there is the so-called precursory fluctuation dissipation theorem, that you have diffusion, so the losses are proportional to the fluctuations, to the temperature, and the beta is here you have viscosity, so you can see it's a viscous force of the per unit mass, so you can see that this is this beautiful formula, there is just one scaling factor, and then his main achievement for the first time appears, the probability distribution that the particle moves from x to x plus dx. So it's a Gaussian. Here is time in the denominator, and here it's also, and you can see again the same type of constant, which means the average mean square change of the coordinate per unit time, of course. So this is how to obtain that. To obtain that, oh gosh, what's happened? Okay, this is the diffusion, this is this Smoluchowski probability function evolution. This is Smoluchowski equation, which is probably, I have used it 20 few years ago in the quantum aspects. What is the important here? This is what is the difference between Fokker-Planck and Boltzmann equation and Smoluchowski equation. Fokker-Planck equation deals with the evolution of distribution function not only in space but also in momentum space. So you have dynamics here, since you have overdamped dynamics, diffusion, Brownian motion, coagulation, and so on. So you don't have momentum. You just have time, and you have thermal derivatives. And here is force per unit mass if it's forced evolution. And then, of course, there is this Smoluchowski coagulation equation, which you know better than me. For example, he wrote very beautiful. His papers were crystal clear mathematically. Everybody, even people like Sommerfeld, like Boltzmann, and so they really thought these are beautiful. Then, for example, he introduced the formula for probability of having n particles in volume V. It's a Boltzmann distribution with median in the long time limit. He introduced also probability of observing n particles. At an instant earlier, there were n. He introduced what the Poincaré recurrence time estimated in terms of time when the particles do not change, stay n via the probability of having n particles and so on, and many, many other things. Final remarks. First of all, the highest award of Polish Physical Society is the Smoluchowski Medal in Physics. It's no money involved, it's a very beautiful golden medal. There is annual Smoluchowski Statistical School in Zakopane. You can look at our university page, and there is Smoluchowski name also appears a lunar impact crater on far side, which means on dark side of the moon.
Which in fact is close to the point where American landed.
Yes. You spoiled my show, huh?
I'm sorry.
Okay. There are two references. One is, as you know, Chandrasekhar. This is the Chandrasekhar of black holes. He wrote a beautiful article about Smoluchowski theory of statistical process. Mark Katz also comes from here and was habilitated in Krakow. You see, those two universities were in permanent contact. These are only 450, just you go around, move 450 kilometers westward, and you are in Krakow. And then Andrzej Fuliński, actually he should be the person, retired professor, who should talk about Smoluchowski, and there is his article in Acta Physica Polonica B, where normally high energy physics appears, but that's what it is. So, Jagiellonian University started at Wawel Castle, Royal Wawel Castle. Collegium Maius was a little bit later. So the King Casimir the Great first lectured. So even in medieval times, education was being appreciated. If you don't like this thing, then you have the night impression of the Royal Castle of Wawel. And then I leave you with this man. Thank you very much. I presume there are no questions. There may be many questions for which I cannot answer.
Really part of the receptive fields of our human eye, right? So for this reason, the strong light intensity coming from those regions over here is inhibiting the signal that is being sent to our brain, right? And therefore, there is this illusion as if there would be those darker dots in those regions, right? Whereas if we now consider this region in between the two black squares, right, we have fewer regions of high intensity, light intensity around them, and the signals are not being inhibited that are being sent to brain. Does it make sense? More or less, we understand why, right? It all depends on the surrounding. Just like when we deal with the frame of a picture, right, in a case of darker frame, the picture will look lighter and vice versa. So here we have those kind of dark squares in different regions of this grid. The intensity is being inhibited differently. All right, as we perceive it with the retina. All right, and so in here is one more example. So this is now lateral illusion that's involving lateral inhibition in this case. And so you probably, who can tell me what you see here as you look on this on those stripes? What do you see? Are those of the same intensity as you would go from left to right? The intensity is changing, right? How is it changing?
Looks like it's getting lighter.
It's getting lighter from as you would go from left to the right, right? Would everybody agree? Okay, so even though all of those stripes have equal intensity from left to right, but this is how we perceive those stripes, right? And the reason for this is exactly similar to the previous case. So because the adjacent bars, which in all cases have homogeneous intensity from left to right, but all bars from left to right appear to be are darker, right? And so for this reason, the signal is inhibited more strongly from the left side and less from the right side, right? Because the stripe on the right is always darker, as we would go from left to here. Does it make sense? And so for this reason, each individual stripe, as you would go from left to right, appears to be darker on the left and brighter on the right. Make sense? Now, if we would somehow encircle different regions on those stripes, we would realize that intensity actually does not change, right? So if we change this surrounding, then we realize that the stripes are of actually homogeneous intensity along the width of the stripes. Now, in here is one more example showing the enhancement of perceived intensity by changes of intensity at the edges. And so, what can you tell me about the stripes? Focus your attention only on the central regions of the stripes, right? So, what can you tell? Intensity of this stripe here in the central part as compared to this stripe over here. Which one is lighter? This one or this one? One on the right? Appears to be lighter, right? However, if we now hide those edge regions, we realize that they are of exactly the same intensity, right? As you can see here. In here, you still see them being of different intensity because there are those edge effects, right? And so, if you now remove the effect, is working once again. So once again, just because we have light intensity changing in here at the edge being darker, and in here at the edge the stripe is lighter, we can control the perceived intensity of those stripes. So for this reason, this stripe appears brighter. All right, so in here we just discussed, so far we just discussed the edge effects, and now we would like to consider some other effects related to perception and human vision, and those will be now related to temporal perception. And so here's one example shown on the right. If you would focus your attention on the tiny dot over here, right? If you would look on this image for a very long time, again, it might work not so well if you look from very far away in this lecture hall, but if you would look on it from a close distance at least, then what will happen is that in the part of the image which is brightened here, the corresponding, so if you will stare on this image for a very long time, on the same point, right? So the light intensity from this part of the image will fall into the same receptive fields in the eye, on the retina of the eye, and so and so they will become inactive after some time. On the other hand, the dark part in the dark part of this region, there will be not that much light falling to the corresponding receptive fields of the human eye. And so those receptive fields will be stimulated differently. And so, if you would then look on the left part, you will realize that because different parts of the receptive fields in the retina were stimulated differently, you will kind of see the after image of what you saw on the left, right? I mean, it's difficult to do it when you have a small image on a screen far away from you, and that's why I do not ask you to try it right now, but I recommend that you do it in your home. So as I mentioned it once again, in the bright parts, in the parts of the retina corresponding to bright parts of this region, the receptive fields will be less active, and on the other hand, in the dark parts, those will be active, and therefore once you switch your look into the left and into the right side of this image, you will be still able to see what you saw on the left on the left side of this image. However, if you would rapidly blink your eyes, you should be able to get rid of this after image very quickly. So now we will proceed to other types of temporal perception and our vision related to temporal perception. But before we do this, I would like to remind you about stroboscopic photography, which we mentioned it when we were covering the chapter on photography. So if you would like to take images of various objects in motion, you remember that we needed to expose those objects with light of strong intensity, right? And we also needed to have the exposure time being very small, right? So in the case of stroboscopic photography, it's possible to take many images very quickly. For example, one image could be taken in just 1 microsecond or so. As I mentioned, for this we need very strong light intensity, illumination with intensity of with light of large intensity. And so in this case we can take multiple images. For example, every so one image would correspond to just 1 microsecond time duration or so. And then we can take multiple images and from those reconstruct motion, for example, as shown in here on the image on the right part of the screen. With this stroboscopic photography, it's also possible to take photos of objects in motion. For example, one of those you can see in here where the bullet is going through the apple, and we are able to stop even this motion picture to freeze it, even though we know that the speed in here is very high. And so now I have a clicker question for you, and the question is, in the image over here, I hope it's visible for you from different parts of this room, how was this composite photo taken? Right, so you basically see the person in different so I will start the system right now, and please start quoting. So A, B, or C? I'll stop here and we'll display the results. Oh. So most people answered B. By leaving the shutter open and flashing the strobe light many times. This is the correct answer. And who would like to explain why he answered this way? Yes?
Because like you leave the shutter all the lights on white, and with a strobe light, it's just gonna get black, and it just whatever's flashing the light.
Maybe you could say it more loudly, because I could hear you, but I doubt that people in the other part of the room.
With the strobe light, it's just going to be, you're going to get images of what's flashing in front of the light when the light's on, and then the blackness in between is whenever the light's on.
You wanted to answer to?
Yeah. Did you say it was a composite photograph?
Yes.
That would mean that they were taken individually and then processed together.
And then you would put one on top of the other.
Yeah. So that would mean that A would also be true.
Well, the only problem with A is that mechanically it's very difficult to open and close the shutter so quickly. But, you know, so in any way, we will proceed now, and basically you do not need it, right, in this case. And so, with that, we would like to proceed to learning about movies and television and how those work. And they are also related to the way we perceive images. I think that I want to show the following slide first. So, in the case if we, for example, would like to perceive an image, right? So there is some intensity from objects around us, intensity of light coming to our eyes. What's the response of the eye to these rays of light? In the case if we have, the time axis over here, and this is a brief image, so basically just like in the stroboscopic photography, there is some flash of light coming to our eye, right? Some rays of light over some time, very tiny fraction of a second, for example, coming to our eye. We will be able to perceive this image with some delay, which is again relatively small. It's a fraction of a second, and then an after image will be formed. So after that, we will perceive the image, just like shown in here. And so this is what I try to demonstrate for you, right, by this kind of animation. So here we flash the image to our eye, just like that, for very short duration. And then what we see is after image, which is delayed for a small period of time, just like shown in here, right? And then we see this image for some time. Not forever, of course, right? But there is some finite time during which we see, we perceive this image. And so this is important from the point of view how we perceive movies, and the reason for that I will describe in just a second. So this is the graphs over here show the typical response of the rods and also the cones when we perceive the images using cones or rods. And as you remember, we use cones in the case if we have good a lot of light, and if it's dark, we usually, during the night, for example, we perceive using the rods. So as you can see, if there is in this instantaneous image that we are looking at, right, at the time 0 over here, then the response is such that in a fraction of a second, the light-sensitive rods and cones start forming image in our eye, in the retina of our eye, and then this image persists for some time in the case of cones and also in the case of rods, but it persists for much longer time in the case of rods, right? So the image that we see in the case of dark room conditions, after it had been shown for us for instantaneously small amount of time in here, we see it for much longer time, right? And the delay is somewhat longer, as you can see. But the delay is relatively small in the case of perception with cones, and still this image is present for some time, as you can see in here, right? And then after that, we see nothing once again. So how this is important from the point of view of television and our ability of seeing movies. So in the case if different after images overlap with each other in time, just like shown in here, we will simply see a continuous image, right? That's why we see, we perceive things around us continuously, because different after images overlap with each other in time. In the same way, if we will be showing those images, the frames, for example, in television, at each point of time in here, and then if the frequency at which those images are being shown to us is such that the after images overlap with each other, then we will see it as a continuous image of a movie. So if the images rapidly succeed each other, then they are blended into a motion picture. And this is exactly what is used in the television, because the frames, different images are being shown to us at the frequency such that the after images overlap with each other. So the persistence of vision for human eye is relatively short. It's only 1/50th of a second. And so for this reason, we need to show those images that will form motion picture more frequently than 1/50th of a second, so that the images will be blended into a single motion picture or a movie. Apparently, in the television, there are different pictures shown every 1/24th of seconds, so 24 frames, different images per second are being shown in movie, the same frame is being shown 3 times, right? So this way, the after images of those frames can overlap each other, because per second we see 72 images or so, and that means it's more than 50, so that the after images overlap with each other, and we see a continuous motion picture. So as I mentioned, this is the basis for movies, and I'm sure that you have not seen old type of television when there was some flickering, where you would see the different frames not overlapping with each other, right? And even I have not seen those movies myself. This was very old television. But the reason for this flickering was exactly that we just discussed, because different after images were not overlapping with each other, and in between them you would see something different. And so the way all television works, and also cartoon movies, is very simple. What we see is different frames being shown to us at such frequency that the after images overlap with each other, and therefore we see continuous motion picture. I encourage you to go to the web page, to which we will go right now together, and read a little bit more about television. What we discussed so far here is how we perceive the movies and the pictures shown to us in television, but if you go to this web page, and you will have a link. Sorry about this.
How many frames per second can our eyes see? Or
Pardon?
how many frames per second can our eyes see?
So the after image is 1/50 of a second, right? So in principle, you could see 50 images per second separately, or a little bit less, 49 or 48 probably. This is slightly different for different eyes, but it's roughly this. And in order to blend those images into a continuous motion picture, you need to have the after images overlapping with each other. That's why in the movies we need to see more than 50, right? And so what is the standard is, for example, 72. I just want to show you the web page, but somehow okay, so on this web page you will be able to learn about what old type of television where CRT tubes were used, and also the new types of television where, for example, liquid crystal displays are being used, and also the basic concept. So it's very useful web page for interactive learning of this material. It starts with the old type of television. This is CRT tube, which I'm sure you do not have in your home, right? Because this is very old type of television. But then it goes to more new material. And so, as I mentioned it before, we will not be able to go through all different types of possible illusions, because there are so many of those. And I will very quickly go through them, through those slides right now, but I encourage you to spend some time in home and, focus your attention on the examples that will be given in this presentation. It's just simply fun to know how we perceive different things around us. For example, when you will look on something like this here, stir for a long time, at some moment you will not be able to notice this ring around the dot, the ring or the disc on this image, and the explanation is here, which again I encourage you to read. This material will not be tested. This is just for fun. Also, you can learn about this type of illusion over here, where where you looking at those images, your eye will involuntarily move from the image, as you will be able to see. And again, the reason, the explanation of this type of illusion is in here. Yet the other type of illusion is related to the spatial frequency adaptation. And so, again, after some focusing, you will not be able to notice the difference between those stripes here. And this is just another version of spatial frequency adaptation. There are also illusions related to the size after effect shown in here, and waterfall illusion. Note that even though all these different types of illusions are related to the perception that we discussed before, using the inhibitory and excitatory parts of the field class, some types of illusion are not yet quite well understood, including this one shown in here. And there are also links to the web page. This is yet another type. I hope that this works even if you look from far away in this lecture hall. So if you look for a long time on this central part of the screen, I hope that you see some motion there, even though there is none. And again, I encourage you to spend more time on that in home and see that this works. More examples in here of different types of illusions where, even though we have horizontal lines in here, because of this illusion, they seem to be not horizontal, right? And the explanation, again, you can find on the next slide. I hope it's visible. I hope that it's visible for you that these two horizontal lines seem to be not very straight, right? Even though they are actually straight. And this is yet another type of illusion related to the perception and excitatory and inhibitory parts of the receptive field that we discussed before. Same thing can be is true about those vertical lines over here, even though they are straight, but they do not appear straight as we look at them. And get more examples. So this is all we have for chapter number 7. Are there some questions related to this material? So as I mentioned it, the material in the end of this PowerPoint presentation you can find on the web page. I encourage you to go through it. It's very interesting, but it will not be tested on the exams. And I think that since we have only 5 minutes left, we will resume on next Tuesday.